this is actually pretty simple, which is nice, I think. Gordon sent me up here to maybe raise the confidence of some. I know at least when I was here 2 years ago, I thought this was over my head. It still is. So it's nice to have something that isn't as complicated as a lot of these other issues. And that's what's, I mean, it's kind of nice. There's a lot of challenges with genomic data, especially in terms of filtering and pipelines and whatnot. But when you finally get your data, you know, it all comes back to population genetic theory, which is pretty elegant and in some respects simplistic. And it's nice that when we finally have our data, we can apply some pretty nice, straightforward tests. Of course, you can get really complicated too, but it's nice when you can sort of use population genetic theory to come to some interesting inferences about natural selection. And so, let's see here. I want to open up the data so I sent 3 things, just kind of a Word document that describes a series of steps we'll go through. That's this guy right here. What did I name the data again?
Long test data.
Okay, so like Paul described, I just sent some data from just a handful of populations, just to keep it relatively simple. So these are 3 populations of trout. These are spawning populations. And we usually define spawning populations by stream segments, so these are actually the names of 3 different streams. One of them is Finley Creek. It's about, I don't know, half an hour, 45 minutes south of you. It's a tributary to the Jocko River. The other 2 streams is Cyclone Creek and Hay Creek. They're tributaries to the North Fork Flathead River, which is about an hour and a half north of us. So what you actually have in this data file is allele frequency estimates and associated sample sizes for 9,380 diagnostic SNPs. All of these SNPs are, this is the name of the SNP to the far left, and this name tells you some information about its location in the genome. So these are all chromosome 1, and it goes through that. Some of them are mapped as Paul described. We actually know their physical location in the genome. Some are just on these scaffolds, etc. I'm not going to get too much into that. We're just going to run through the test, but you can kind of just peek and see what sort of data we're dealing with. An interesting little side issue with the long test is that it blows up if you have fixed allele frequencies of 0 or 1. And so these allele frequencies actually aren't the observed allele frequencies. We've adjusted them using a Bayesian posterior flat prior distribution, which essentially just kind of pushes things away from 0 or 1. So far, so good? Go for it.
Were these files on the website or were they emailed to?
They were emailed at lunch. Sorry. Okay, I'll let you maybe have a second.
I don't either.
It's from Jenna.
Yeah, it should be from Jenna.
You don't have it, I just read it too. That would be awesome. Yeah, I don't know.
Are most people familiar with R? Probably. Okay, so I mean, I just have a series of code up there to load my data, all of that good stuff. Obviously, this isn't going to be exactly the same on your computer, so you'll have to change this and change the location of the main data set to run through this script. There's lots of different ways to do that. If anyone wants help, I can help you really fast, but if not, I'll just keep following along. Well, you know, you just run that series of code, and then now we can start to go right into the long test itself. And so, well, I guess really quickly, you know, it's always nice to visualize your data. I think Mike presented yesterday, so he probably beat it into your head that it's important to look at the raw data. I don't know if you did or not, but I assume you probably did. This holds true even at this point. So even after a downstream, I got all these genotypes. I can't tell you how many times we, and by we, I mean a pretty good group of genomicists in this room had to go back and redo the pipeline because by just looking at raw allele frequencies, we noticed some strange things in the data that ended up being problems. So look at raw allele frequencies. They're really informative. So, here's just a little histogram of the observed values of admixture, or just rainbow trout allele frequencies across these 9,380 SNPs in this Finley Creek population. As you can see, there's a fair bit of variation. It's centered somewhere around maybe 0.12, so, the proportion rainbow trout ancestry in this population, in other words, is somewhere around 0.12 or 12%. But there's a fair bit of variation, and what we're interested in is whether or not some of these, the allele frequency estimates at these loci that are, where the allele frequencies are quite low or quite high, whether or not there's evidence that some of that could be due to natural selection. And so, if we are thinking about invasive alleles, because these are rainbow trout allele frequencies, rainbow trout alleles would be at the high end of this distribution. So in other words, it's an allele that appears to be sweeping higher than expected frequencies. But on the flip side of things, there may be some rainbow trout alleles that aren't introgressing at all. In other words, there may be some portions of the genome that are very resistant to rainbow trout introgression. And so, basically, the next little chunk of code I don't know if you actually read the paper that they sent out, the long test, but what's that? Sorry. So this just runs through some of the calculations in that. It's just some matrix algebra. It's really straightforward. If you want to talk about any of that, Paul and I would be happy to talk to you about that, but, doesn't seem to be too necessary at this point. But this kind of just runs through that series of calculations described in the paper. And from there, we can then start to compare the essentially summary statistics to the probability distribution describing this, the heterogeneity in the allele frequencies, which in this case happens to be just a chi-squared distribution, which is nice and simple. And so basically what this next chunk of code does is just calculate some statistical summaries, eventually calculating whether or not the allele frequencies at a particular locus appear to differ significantly from neutral expectation. And this long test, I should have mentioned, it takes into account sampling. So part of this variation we're observing is just simply due to sampling. We have finite sample sizes, and some of it is actually due to genetic drift, and this long test attempts to account for both of these things. So if we run through that, I'm going to actually rename this real quick because I already have this file, so just to complicate things further. You can run that little piece of code. Open this up. So what I did was just write those summary statistics to the allele frequency table. And as you can see, so I just ran it for that first population. And now, in addition to those allele frequencies in the original file, we now have the chi-squared value at each locus, the residual chi-squared value, sort of an effect size here, and the overall p-value at each particular locus. So now this is telling us whether or not the allele frequencies at each one of these loci appear to differ from neutral expectation. Is this all good so far? Cool. And then, we can, now we're home free. We can blast through. If you wanted to, this is a really easy script to modify for your own data, but I'm just going to do the same thing for the next two populations. I've already named them accordingly, but say you wanted to do this for your data, you just grab a chunk of this. This is just for one particular population. You can just easily do sort of a find and replace and change, hey, I've labeled everything by the column allele frequency estimates and the sample size column, but you could easily replace that with your own names, and be able to calculate this really simply if you have this type of data. Really easy. So now, let's see here. Should have written this all to that file. Oh no, it's because I didn't name it. Okay, so now have all of that information for all three of these different populations. And now the next little block of code actually calculates what's called, well, it performs a Fisher's combined test to give an overall p-value for each locus. So, you know, we have some information. I guess it would be valuable to retreat a little bit here. So, clearly, you know, when you have a sample of 20 fish from one population and you start to perform this statistical test, it's going to give us some information about some loci demonstrating some interesting behavior, but it would be pretty naive to assume immediately that well, you know, the interesting allele frequencies are certainly selection. And so kind of the way that we've tried to understand whether this is consistent is to replicate across space whole populations within a basin that are in some ways connected, and entirely different river basins that have completely different sort of evolutionary paths in terms of introgression. And so one way to kind of summarize whether or not we're detecting a consistent signal across space is by combining the information from the p-values and coming up with a global p-value at each locus. And that's the way to combine p-value, and then I wrote that to the same file over here. Okay, there we go. So now we have a combined p-value describing whether or not the allele frequencies, rainbow trout allele frequencies at each locus appear to deviate from neutral expectation. And so now is when we can actually start to delve into the data and have a little bit more fun. But before doing so, it's helpful to keep in mind that, you know, we have 9,380 p-values here. So that is a ton of them. And so it's worthwhile to, well, it's not worthwhile. We're dealing with problems of, you know, you just can't use a simple alpha equals 0.05 because we will certainly be violating, or we have much higher type 1, risk of type 1 errors because of all of these simultaneous tests. So, would it be helpful to show you how to come up with the false discovery rate by hand, like in an Excel table, or should I just do the one line of code and everyone's confident that they know how to use it? Well, I'll just do the simple couple lines of code, but if somebody, I personally really like to take, you know, when I'm doing statistics like this, I'm doing it in R, but I'm often going back to pen and paper or Excel or whatever and double checking all my calculations, because if you've made it this far, you don't want to publish shoddy results because you just made a stupid error in some R code. It's really easy to calculate this stuff by hand, and it's extremely valuable, especially if you're someone like me that makes a mistake 1 in every 5 lines of code. That's how I check myself, and it's really helpful. But you know, R is great because you can just do some very simple commands. Of course, they don't work when you do them.
I think we did this way.
I told you that's.
You're just using a.
That's why I calculate it by hand. Oh, sweet. So degrees of freedom, I didn't mention that. Okay, so just quickly, just to, I kind of summed some things up so you can see. The whole point of the false discovery rate is to, so you can just use sort of a Von-Ferroni correction, but they become extremely conservative. You did alpha divided by 9,380, that's a really small value. And so it actually becomes tough to detect selection. Alternatively, you don't want to just use 0.05 because you're certainly going to be committing false, or your type 1 error, but you don't want to commit, well, and of course, like, this is sort of up to you in your own experiment to what degree you're concerned about type 1 and type 2 errors, but just, you get very different numbers of significant values depending on which of these criteria you use. So false discovery rate's 54, just standard p-value, 900, which actually seems pretty high, and then just the Von-Ferroni is 39. So it just gives you some idea that you need to really think about which sort of criteria you're going to use when you decide what is an outlier. So that's the just simple part, running through the statistical analysis, but the biology is yet to come. And so what I've given you is basically we now have statistical description of whether or not a particular locus is deviating from neutral expectation. But the challenge, or the part of the biologist, is to now go through those data and try to make some sense out of it. And so I guess, Gordon likes to have little exercises. The exercise that I would suggest is maybe just glancing through those data, picking some sort of criterion, actually is really helpful. So the other reason I like to calculate things by hand as opposed to ours, because you can get some nice summary statistics that help you do this, but I can just get my false discovery rate p-value and then create a criterion. And so what the false discovery rate, I'm not going to calculate it, but you want to come up with a criterion for what you think is biologically meaningful as far as your p-value criteria. Look through this and tell me if if there appears to be any interesting stories with respect to natural selection here. And I think there is, and it wasn't what we were expecting when we went into this experiment. And so I'll see if anybody can detect that. And the way you're going to have to do it is p-values are great, right? But at the end of the day, you have to look at allele frequencies. Allele frequencies are what tells you what's actually happening. So that's all I have. Robin?
Yeah, so now we're going to get back here talking about lack of independence of these markers. Some of them have names, so
Definitely.
I'm not sure Von-Ferroni assumes independence, but I'm not sure that at least there's a version out there that I think you can use when there's not
Yeah.
independence.
Yep, that's the idea behind the, I guess I should have just gone with the calculation of false discovery rate, but that is at least the Benjamin and Helfberg, I think is what the name is, that better deals with the fact that they're non-independent. That doesn't mean, that is a good point, is a lot of these statistics that we're calculating do assume independence. And certainly, these data violate that to some degree because of linkage.